Let's get started. Hello, and welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'm Eric Ma, a data science and statistical learning investigator at the Novartis Institute for Biomedical Research. Before that, I did my doctoral thesis work in the Department of Biological Engineering at MIT, where I used network statistical methods to study influenza evolution and ecology. I'll be your moderator today. For those of you who may be unfamiliar with ACM or what it has to offer, here's more information. ACM offers educational and professional development resources that can bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. Firstly, the slides will advance automatically throughout the event. If you are experiencing problems with the slides or audio, you can close and relaunch the presentation. To control volume, adjust the master volume on your computer or mobile device. If you have questions, click the Q&A button on your screen at any time during the webinar. Then, click Ask a Question, type your question, and hit Send. I'll organize the questions as Allen speaks, and he'll reserve time at the end of the presentation to address them. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. Also, check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open up on your screen. Please take a minute to fill it out to help us improve our webinars. Also, feel free to share the webcast link with your friends, as well as tweet comments and questions using the hashtag ACMLearning. We'll be watching for your tweets. We also have a new community discourse page to continue the discussion after this webcast, including questions we won't be able to get through during the Q&A session. Now, today's presentation is the Bayesian Zig Zag, Developing Probabilistic Models Using Grid Methods and MCMC by Allen Downey. Allen is a professor of computer science at Olin College of Engineering in Needham, Massachusetts, and the author of ThinkX series of books, including Think Python, Think Bayes, Think Stats, and several other books related to computer science and data science. Previously, he taught at Wellesley College and Colby College, and in 2009 was a visiting scientist at Google. Allen has a PhD from UC Berkeley and bachelor's and master's degrees from MIT. He writes a blog about Bayesian statistics and other related topics called Probably Overthinking It. Allen is also a member of the ACM. Now, Allen, without further ado, please take it away.
Eric, thank you very much for that introduction. And everybody out there, thank you very much for joining us. If you want to follow along at home, you can get my slides. The URL is here. This is tinyurl.com, zigzag ACM. In particular, later in the talk, I have a Jupyter notebook that has my code and all of the examples. So there are links to that are in the slides. So if you get the slides, you can get to the notebooks. The thing I'm talking about today is Bayesian statistics. And this is one of my favorite topics because they are powerful and useful. But for a lot of people, it is hard to get started. This is a page from one of the most popular books about Bayesian statistics. This is just page 7. So this is a little bit intimidating. What I'm going to talk about today is a Bayesian Zig Zag. This is an approach that I think is good for learning about Bayesian methods, but also for developing models iteratively so that you can validate them as you go and believe that you've done it right. The zigzag part is going back and forth between forward and inverse probability. What I mean by that, forward probability means that you have a model of the system and somehow you know the parameters of the system. So you can run it forward and you can generate data as if they come from that system. Inverse probability means going in the other direction. So you have a model of the system, you don't know the parameters, but you observe the data coming out of the system, and inference, you infer what the parameters of the system are. So the zigzag suggests that we're going to start by going forward. So we're going to simulate the model and then run backward using grid approximations. And I'm going to explain what that means. So now you've inferred the parameters. You can now use those parameters to run the model forward and generate predictions for what is going to come next. And now part of the reason that I think that this is useful is that the forward model looks very much like the PyMC model that we can now use for doing inference. So we go backward now using the PyMC model. So now we have two models doing the same thing. We can validate by doing comparisons between the two of them, then use PyMC to go forward one more time. So let me show an example of what I'm talking about. If you are a fan of the Boston Bruins, you know that they have a game coming up on Friday against the Anaheim Ducks. And if you've been following the season, you know that they played in December. And in December, the Bruins won 3-1. So I'm going to use the data from the previous game to make inferences about the two teams. And then I'm going to use that to generate a prediction for Friday's game. And in 2 days, you can check to see whether I got it right. Now, you might not be a hockey fan, and this might sound like a strange example. Fortunately, everything I'm talking about today applies not just to hockey, but to any system that is well modeled by a Poisson process. So a Poisson process, the fundamental idea is that these events are equally likely to occur at any time. And if that's true, or at least if it's approximately true for modeling purposes, then we can answer questions like, how long will it be until the next event? Or how many events will there be in a given interval? So in this example, the events are goals scored in a hockey game, and the prediction we're going to make is how many goals do we expect in the next game. So we can get into it. Again, if you don't have the slides, you can get them from tinyurl.com. Zigzag ACM. And that will get you to these two links, which will get you to a Jupyter notebook that contains all the code. If you use the GitHub link, you'll get a static view of the notebook. So you'll see the code and the output, but you won't be able to execute the code. If you use that binder link, you will get a live view of that notebook. You can run the code, you can change it, you can try out other examples. And you can do that now or anytime in the future. I'm going to show you most of the Python code to run these examples. If you know Python, I hope this will help you understand what's going on. If you don't, I think it's very readable. Almost every step is just a few lines of code, and they're all using standard Python libraries like NumPy and SciPy, and particularly PyMC. So if you see the code, don't panic. Okay, first step, running forward, I'm going to simulate a hockey game. So let's assume that the probability of scoring a goal during any minute of the game is P. And as a modeling simplification, I'm going to say that we either score a goal or don't. It's not possible to score more than one goal during any particular minute. And I'm also going to assume for now that we know the probability of scoring a goal during any minute. So I'm going to simulate a 60-minute regulation play of a hockey game. This is a Python function that does that. The parameters are P, again, that's the probability of scoring a goal during any minute. And 60 minutes is the duration of an NHL game. I'm using a NumPy function, which is random.choice. It's going to choose either 0 or 1 goals. It's going to do it n times, so 60 minutes. And during each minute, it's going to use 1 minus p and p as the probabilities. At the end of the game, I'm just using np.sum to add up the total number of goals. And if I do that, let's say 1,000 times, I can estimate what the distribution of goals scored looks like. This is the probability mass function, showing that most of the time you're going to score between, let's say, 1 and 4 goals. 0 is unusual. Values greater than 4 are unusual, but not impossible. So I simulated that using a discrete model. I can also fit it using an analytic model. And in this case, the actual distribution is binomial because I chose n values with each one having an independent probability. But that's well approximated for these parameters using a Poisson distribution. And I can show that here. I'm going to use the NumPy function that generates random values from a Poisson distribution with the parameter mu, where mu is the goal scoring rate. How many goals do we expect to score per game? And that's the product of n and p, the number of minutes, and the probability of scoring. So this is a sample from the same distribution we were just looking at. And I can compare the results from the simulation and from the analytic Poisson distribution. Looking at the PMFs, they are similar. They're not exactly the same because of some random variation. I'm going to suggest, though, that we look at cumulative distribution functions rather than probability mass functions. And that's what I'm going to do for the rest of the talk. So this is the same data shown using a cumulative curve. These are the same probabilities. I've just added them up. I think this gives a better view of the two distributions and a better ability to compare them, see where they differ and how they differ. And the point of this is that I'm getting mostly the same results from the simulation and from the analytic distribution. Okay, so far this is all forward probability. Somebody tells me what the parameter is, mu, and I can compute the distribution of goals conditioned on mu. For inference, I want to go the other way around. I want to compute the distribution of mu, the parameter, for a given observed number of goals. And Bayes' theorem tells us how to get back and forth between those two things. Bayes' theorem says on the right-hand side, if you know the conditional probability of B given A, you can compute the conditional probability of A given B. So that's what this inverse step is going to look like. I'm going to do a Bayesian update, which means I start with prior beliefs. That's the distribution of mu, or another way to say the same thing, it is the probability of mu for each possible value of mu. So starting with the prior, I'll compute the likelihood function, which is the chance of getting a certain number of goals given mu, and then use Bayes' theorem to get to a posterior distribution, which is the probability for each value of mu given the observed data, the observed number of goals. Here's what that looks like in code. So this is a function that does a Bayesian update. It takes a suite and data and a likelihood function. So the suite is a suite of possibilities. It's a dictionary that maps from each possible value of mu to the probability of that value. And I'm going to do an update by modifying the suite according to the data that I've observed, which in this case is the observed number of goals. What I need to do that is the likelihood function, which computes this conditional probability, the chance of seeing a certain number of goals given a hypothetical value of mu. So the way this function works, it loops through the suite and it pulls out each hypothesis, each hypothetical value of mu. And it computes the likelihood of seeing the data for that given value of mu and multiplies that by the prior probability of that hypothesis. So the result of that loop is a posterior distribution that is not yet normalized. Those probabilities in general won't add up to 1, but I can make them add up to 1 just by computing the total and dividing through. And that's what normalized does. So the result of all of that is the posterior distribution. The last piece that I need is the likelihood function. And we've already figured that out. We already said that the probability of seeing a certain number of goals for a given value of mu is just the Poisson PMF, the probability mass function, of the observed number of goals conditioned on the observed, the hypothetical value of mu. Okay, so I've got a likelihood function. I need a prior. That is, what do I believe about mu before I see any data? And mu, again, is the goal scoring rate, the number of goals I expect in a given game. Turns out that a gamma distribution is a reasonable choice for this model. The shape makes sense for hockey games, and I can use data from past games to estimate the parameters. So I've done that, and it turns out that with the parameters alpha equals 9 and beta equals 3, we get a prior distribution that captures what we believe about hockey games in general. I'm going to evaluate that gamma distribution for a range of values of mu. So I'm using linspace here, which creates equally spaced values between 0 and 15. And in particular, it creates 101 of them. And it creates an estimate of the gamma distribution. Now, it's not exactly the gamma distribution because mu is actually a continuous quantity, but I'm approximating it with a grid of discrete values. And that's what I mentioned at the beginning. This method is called a grid approximation, where I take all of my discrete values, all of my continuous values, and approximate them with a discrete grid. Here's what that prior distribution looks like. And this says that between any two teams in the NHL, I think that the goal scoring rate is probably near 3. If it's the best team against the worst team, it might be as high as 6. If it's the worst team against the best team, it might be low, less than 1, but it's probably in this range. Now, I can use that function to do the Bayesian update. I'm going to take my prior, I'm going to make a copy before I modify it, and then run the Bayes update function. For this example, let's pretend that we've seen a game and one of the teams scores 6 goals against the other one. So I'm going to take that observed data plus the likelihood function that we were just looking at and do the Bayesian update. Here's what the results look like. That blue curve is the prior before I saw the data. The orange curve is the posterior. This is what I believe about mu, the goal scoring rate, after seeing one game where 6 goals were scored. And the orange curve has now shifted off to the right, off toward higher values of mu, and that makes sense. You scored more goals than I expected, so I think mu is probably higher. Okay, so we've done inference. We've got from data to a posterior distribution that represents what we know about mu. The next step is to make predictions. So for this game coming up on Friday, I would like to predict the number of goals that each team will score against the other. So now we're back to doing forward probabilities. I'm going to do this by random sampling again. So I'm going to draw a random choice from the posterior distribution of mu. That tells me a hypothetical goal scoring rate, and then use that as a parameter to a Poisson distribution to get a predicted number of goals for the next game. And if I do that, say 1,000 times, I will get an estimate for the posterior predictive distribution of the number of goals. Here's how I do that. Remember that this suite, this posterior suite, is a dictionary that maps from each possible value of mu to its probability. So I'm going to use NumPy random choice again to draw a sample from the possible value of mu, the mu's, M-U-S. I'm going to draw n of them, a sample size of n, and I'm going to choose them with probabilities p. So those are the probabilities that correspond to mu in the posterior distribution. That sample post is a sample of mu's. If I now pass that as a parameter to NumPy random Poisson, I get the predictive distribution, which is a sample of possible goals for the next game. Here's what that distribution looks like. So again, this is what I should believe after seeing the first game. These are my predictions for the next game. This distribution represents two sources of uncertainty. So first of all, I don't actually know what mu is. I have a range of values for mu, and I have probabilities for those values, but I don't know what mu is. And even if I did know mu, I would still be unsure about how many goals we're going to score in the next game. Okay, so that used the grid algorithm to generate a predictive distribution. Now I'm going to do the same thing using PyMC, which is a strange thing to do. This is not really what PyMC is for, but this is going to help me get these two models talking to each other. So I can validate that the model makes sense, and I can verify that I've done my implementation right. I've implemented the model that I intended to. Here's what PyMC looks like. To create a PyMC model, I'm using PM, which is the import for PyMC, creating a model object. That model object is going to contain all of the variables in the model. And then inside the model, I'm creating two variables here called mu and goals. Mu is my prior distribution for mu. It's a gamma distribution with parameters alpha and beta. The next step is to create goals, which is a Poisson distribution. And the parameter for goals is the mu, the other variable that I just created. So that's how these two variables are connected to each other inside this model. Now I'm going to use a function provided by PyMC, which is called sample prior predictive. And this is going to generate a sample from the prior distribution of mu and the prior distribution of goals. And I can confirm that I get the same thing in blue. That's what I got from the grid algorithm. And in orange, this is what I get from PyMC. And this is telling me that I've got the same model in both implementations. And similarly, this is the prior predictive distribution for the number of goals. Again, these two models are the same. So this makes me feel better about the model. It also helps me with the next step, which is to use PyMC to do inference. So I'm going to go backward one more time. And the reason I went through all of this is that this model, which specifies the forward problem, looks very much like this model, which specifies the inverse problem. So this model does predictions, and this model does inference. And the only difference between the two is that in the first case, goals is a predictive variable, and in the second case, it's an observed variable. I've seen, let's say, a previous game where one of the teams scored 3 goals. So I specify that goal is observed, and instead of using sample prior predictive, I use sample. And what sample does is runs the MCMC algorithm to sample from the posterior distribution of mu. And again, I can take the results from the grid algorithm and compare them to the results from PyMC and confirm that I'm getting the same thing in both cases. The last step, now that I've got PyMC, I'm going to run the PyMC model forward. Here's what that looks like. I've got a function that's called sample posterior predictive. It takes the result from the previous step. That trace is the sample from the posterior distribution. And what this function does is it generates a sample from the predictive distribution. And here's what that looks like. And again, I can compare it to the results from the grid algorithm and confirm that my model works. The nice thing about this, I now have 2 models where I've got some confidence that they're correct. The reason this is useful is that PyMC is capable of working on much bigger problems than grid algorithms. Grid algorithms, I think, are a good way to get started, but you will eventually get to a point where they won't work for you, particularly if you have a large number of parameters. Once you get past 2 or 3 parameters, grid algorithms can't handle that anymore, but PyMC can, and this is a gradual way to get into it. So that was the zigzag. We've got our 5 steps going back and forth between forward and inverse probability. Just to finish it off, I want to come back to the motivating question, which was to make a prediction for Friday's game. So I'm going to take that PyMC model and extend it to 2 teams. I'm going to estimate separate parameters for Boston and Anaheim, and 2 pieces of data. In this case, from the previous game, Boston scored 3 goals, Anaheim scored 1. Here's what that looks like in PyMC. I've got 2 values for mu, 1 for Boston, 1 for Anaheim, and 2 values for goals, again, 1 for Boston, 1 for Anaheim, with the observed data there. So observed equals 3, observed equals 1. And now I'm going to run sample, so that's the inverse problem. That's going to estimate the posterior distribution for mu, having seen this data. And here's what that looks like. These are the distributions of the goal scoring rate for Boston in blue on the right and Anaheim in orange on the left. And having seen 3 goals to 1, I now think that Boston's goal scoring rate is higher than Anaheim's goal scoring rate, and these distributions tell me by how much. I can use them to compute the probability of superiority, which is what's the chance, having seen that first game, that Boston is a better team, meaning higher goal scoring rate. And I can do that just by taking my sample of mu from the 2 teams and comparing them element-wise. So each random sample I want to see is the estimated value for Boston greater than the estimated value for Anaheim. That happens about 67% of the time. So I would say that there's a 67% chance, based on this data, that Boston is a better team. It has a higher goal scoring rate. Last step, I can use that trace to generate a predictive distribution for the next game, the game coming up on Friday. This is the number of goals I think Boston will score and the number of goals that Anaheim will score. Here's what that looks like. As you would expect, I think Boston is the better team. Therefore, I think that they are more likely to win. And this distribution tells us the probability for every pair of goals that might occur on Friday. I can pull out of that the probability of winning. So I can compare the number of goals for Boston, the number of goals for Anaheim, and see if I think Boston will win in regulation time or lose, or whether the score will be tied. And it looks like it's about 48 or 49% that Boston will win, maybe 33% that they will lose, and 18, 17% of going into a tie. Just as one last step for fun, if it does go to a tie and it goes to sudden death, then whichever team scores first wins the game. And we can predict the time until the first goal. That distribution is an exponential distribution with the parameter 1 over mu. So in the same way that I used the posterior distribution of mu to predict the number of goals, I can also predict the time until the first goal for both teams. Here's what that looks like. So TTS means time to score, and I'm going to select random values from an exponential distribution with parameters 1 over mu for each of the values in the sample that I generated. And this says that the probability of winning in overtime is the chance that the time to score for Boston is shorter than the time to score for Anaheim, and that's about 55%. The grand total chance of winning is the chance of winning during regulation time, plus the chance of going to a tie and winning in overtime. And that is about 58 or 59%. So to summarize, first of all, go Bruins. Second, if you would like to learn more about this example, this is based on Chapter 7 of my book, which is called Think Bayes. Chapter 7 presents the Boston Bruins problem. This book is available under a free license from thinkbayes.com, so you can read it online. It's also available in hard copy from O'Reilly Media. One last thing I want to say is, I think that this example is fun, but I would encourage you not to use this kind of thing to go and gamble. First of all, it's not very good. In this example, I only used data based on one previous game. I'm not using a lot of information, so it's probably not a very good prediction. But the other reason not to gamble is that gambling is a zero-sum game, or less than zero-sum. If you do a really good job and you win, you are just taking money away from someone else. You're not actually creating value. I would encourage you, if you have made it this far into the talk, you probably have some skills that you could use for things that are better than gambling. And in particular, I would encourage you to allocate some time to do data science for social good. I want to point you to a couple of links. If you get my slides, you'll see a number of organizations that you could work with. But I also, if you follow this link, this is an excellent blog post by Diego Arenas, who has collected a lot of resources for doing data science for social good. So I encourage you to read that. Last thing I want to say is a thank you to Chris Vonnesbeck, who is one of the developers of PyMC, who helped me develop the examples I was presenting. Colin Carroll, who is not only a PyMC developer, but also added a couple of functions to PyMC just in order to make it easier for me to make these examples work. And finally, a thank you to Eric Ma, who is our moderator today and also a contributor to PyMC. One last time, the slides are at that URL if you want to grab them. And if you want to get in touch with me, these are a number of different ways that you can do that. So I'll stop there and take any questions. Thank you.
All right. Thank you very much, Alan. We're now going to go into the Q&A portion of today's webinar. We've had a lot of discussion, both in the chat window and questions coming in via the Q&A panel. And I've already marked a few questions that I'd like to have answered live because I think it'll be valuable for everybody to hear Alan's answers on these. So we're going to start first with a question which a lot of people have been asking. Alan, how would you choose prior and likelihood distributions? What kind of things do you have to consider?
Great questions. So both of those things, the prior and the likelihood function, are modeling decisions. And they come from all the background information that you have about the system that you're modeling. Usually the likelihood function is more straightforward. It often comes directly from the description of the system. In this case, the model I'm using is a Poisson process. And that tells me that if I want to predict the time until the next event, the distribution is exponential. And so my likelihood function in that case is the exponential PDF. And same thing, if I'm predicting the number of goals, the model tells me that that distribution is Poisson. And so my likelihood function is the Poisson PMF. So the likelihood function is a modeling decision, but it's usually mostly uncontroversial. When people disagree, they usually disagree about the priors. And that's because they're often working with different background information. In this example, we've got every other hockey game that we could go and observe, and we could use that to estimate, how often does a team score 15 goals in an NHL game? It's extremely rare. I don't know what the record is, but it might not even be 15 goals. And that's going to tell me, okay, I can put an upper bound on it. And how often do shutouts occur? They happen, but they're not super common. So that information, my knowledge about hockey, would at least allow me to sketch what I think the prior distribution looks like. And often that's a good way to do it. If you can qualitatively describe the distribution, then often you can take that qualitative description and turn it into a quantitative representation. In my case, I chose a gamma distribution for a reason that I didn't mention, which is that the gamma distribution is the conjugate prior for the Poisson likelihood function. Now, I didn't actually take advantage of that. That turns out to be useful for doing analysis, but I didn't do any analysis. So I could have used any distribution that had a reasonable shape and that describes what I know about hockey games. Maybe I'll stop there and see what other questions we have.
Cool. Yeah. Thanks a lot, Alan. So about the choice of priors, I think there's a lot of people that have questions about that as well. Are there particular priors that can completely ruin one's analyses or cause issues, say, for example, when we're doing MCMC sampling?
Right. Okay. So there are two issues there. One is, a prior that will cause you to get the wrong answer.
Mm-hmm.
And that, in general, one of the properties, mathematically, what's going on here is that we are taking the prior and multiplying it by the likelihood.
Mm-hmm.
If the prior is 0 for any value of mu in this case, and you multiply 0 by anything, the result is 0. And what that's telling you is that if you rule out a hypothesis, no amount of data will ever change your mind.
Mm-hmm.
So as a general guideline for choosing a prior, you should avoid giving a 0 prior to anything that is even conceptually, logically, infinitesimally small probability.
Mm-hmm.
Just don't give it 0.
Mm-hmm.
As long as you do that, you should get the right answer given enough data. Enough data will eventually get you to a posterior distribution that is at least approximately correct, approximate, up to the quality of your modeling decisions.
Okay.
So that's part one about choosing the prior. The other thing that you mentioned is issues with both grid algorithms and PyMC.
Sampling, yes.
And they're just algorithmic considerations
Mm-hmm.
for making sure that those algorithms behave well. In the case of grid algorithms, you have to make sure that you put the grid in the right place. In other words, in the part of the probability space that has a decent amount of density, and that the grid is fine enough, that the precision of the grid is enough that you're getting an accurate estimate of the posterior. So that's with grid algorithms. With PyMC, there are other issues with making sure that the Markov chain can move around in the probability space and find the places where all the probability density is. Mm-hmm. And the shape of your prior can either help or hurt with that. The way you specify your model can make it easier or harder for the MCMC algorithms to work. Mm-hmm. But that's getting into a level of technical detail that we can't talk about much today, other than just to make people aware of those issues.
Definitely. Okay, thanks, Allen. I might add one point as well, in that from personal experience doing Bayesian modeling, it's been useful to think about, so when Allen mentioned 0 as a prior or 100% as a prior, those are pretty extreme priors. They're very narrow. They reflect a narrow mind. In general, we tend to think about weakly informative priors as being something that's pretty helpful in Bayesian modeling. So we might not say, let's start with a normal distribution as my prior distribution with variance of 0.01. We might give it some amount of variance, but still it comes back down to a modeling decision, just as Allen mentioned. So here's another question that is pretty interesting. I like this one because it asks about what problem classes are useful for Bayesian approaches, and when might you want to avoid a Bayesian approach?
Good questions. Bayesian methods are particularly good when you have a small amount of data, because they are good at wringing out of that data all of the information that's available and combining what you learn from the data with all of the background information that you can bring to bear. So that's one, I would say, category of problems where Bayesian methods help. The other is thinking about what you want to use the results for. If you are making decisions based on this analysis, Bayesian methods are useful because the result is represented in the form of a posterior distribution that you can use as part of a decision-making process. So if all you get from your statistical analysis is a single point estimate, like I think that the Bruins will score 3 goals, that doesn't necessarily help you make a decision. In this example of betting, for example, I would want to know the probability of winning in order to decide whether a bet is a good bet or not on the basis of the offered odds. But more generally, what I want to do is take a posterior distribution and feed it into some kind of cost-benefit analysis, where I can loop through every possible outcome and compute the cost or the benefit of that outcome and the probability of that outcome. And now if I'm making a decision between two different predictive distributions, I can choose the one that has the properties I want, maybe the highest average value, or the highest probability of exceeding some threshold, or the highest probability of avoiding some very bad outcome. So Bayesian methods are really useful for feeding into other kinds of decision analysis. And then the last part of the question is, when would you want to avoid Bayesian methods? So the nice thing about Bayesian methods is that in some sense, the answer is just right. The answer is what you should believe about the world, having seen the data, assuming that your prior was a reasonable model and assuming that your likelihood was a reasonable model. So when would you want to avoid that? Really, the only time you would want to avoid that is if it's either impossible or impractical. And it could be impossible just because it's too big a computation. More likely, it's impractical just because Bayesian methods tend to be computationally expensive. So if you run a Bayesian method, you do the expensive thing. Now you are confident that you know what the right answer is. Again, subject to your assumptions, but you know what the right answer is. Now you might need to find something that is faster, that you can implement in practice, that you can put into a data analysis pipeline, that's live and fast and all that. And so then you might want to use the Bayesian model as a springboard to an optimized model that you can validate and speed up as much as you need to for practical purposes.
Yeah, definitely. And one place where you can actually play pretty fun tricks there is if you have a model that is basically a binary outcome, a 1 and a 0, and you're just trying to predict the probability of 1 versus probability of 0, there are fancy math tricks that Allen alluded to with conjugate priors that let you update the prior distribution directly through some simpler math without having to do any fancy MCMC or grid sampling methods. So for example, the Bayesian update on a beta distribution prior for the Bernoulli likelihood is simply an addition of number of successes and number of further successes and number of further failures that you've observed in your system. So next question is a really interesting one, Alan. How do we use grid methods or sampling methods if we don't have an analytical form to describe our distributions?
Right, that is a great question. All of the examples we've talked about so far do have analytic forms. In the case of grid algorithms, it is relatively straightforward because the likelihood function that you specify can be an arbitrary function. It doesn't have to be analytical. In fact, your likelihood function could sneak out and do simulations in order to estimate probabilities. It could be a non-parametric thing. It could be really anything. The same is generally true of PyMC, but actually, Eric, I'm going to defer to you. I think you can probably answer this one better than me.
So truth be told, I haven't had to do anything with non-canonical distributions. However, one thing that I know is a really neat property of distributions is you can mix them together and obtain fancier distributions that might model something about the world that you think about. So for example, if you have data and you look at it, and you look at the CDF or the PDF and it looks like it's got 2 humps, then you can probably start thinking about a process that involves two normal distributions generating parts of each of the humps. And then you can generate a mixture distribution, for example. And then by casting your non-analytical distribution in the form of, say, a mixture of analytical distributions, that gives you a lot of, I guess, flexibility over there as well. Hopefully that answered the question. Alan, do you have anything else to add to that?
Yes, no, I think that's a great answer, and maybe even to take it one step farther, you could take any amount of data and fit a distribution to it by forming a mixture in the way that you just described. And in fact, if you take something like kernel density estimation, KDE, that's basically what KDE is. It'll describe a distribution as a mixture of Gaussians, or a mixture of any other kernel, but sometimes Gaussian.
Yeah, okay. So another question that came up concerns the use of grid methods. And I think this is also interesting because grid methods are really much easier to understand, and the way you've presented it in your books, Alan, is really excellent for teaching purposes. And so I think what people are curious about is how would you change your use of grid methods for things like non-binary outcomes, say continuous outcomes, or for example, multi-class classification models and that sort of stuff. What are the, I guess maybe part of the question is also, what are the key ingredients that you need, maybe just re-summarized for using grid methods? And how would one use grid methods maybe as part of a toolkit in their analytics workflow?
Right, good question. So they do generalize pretty well. Anything that you can describe using a probability distribution. So if you're doing any kind of a classification problem, you can have as many classes as you want. What your prior would say is, for each class, here's the prior probability of being in that class. And the posterior would just give you an updated set of hypotheses that says, I now think that class C is the most likely and class D is the least likely, or whatever it is. So as long as you can represent a prior using a probability distribution, and as long as you can compute the likelihood function that tells you what would be the probability of seeing the data you saw for a given hypothetical value of the parameters. Those are the two pieces, and they're very general. You can solve, almost any probabilistic problem you can think of, you can fit into that framework.
I see. And so just to go back to that then, actually, the question about non-analytical distributions means if I have a way of assigning probability across my weird mixture distribution, I don't even need to worry about mixtures. I can manually assign probability points across bins of my data then. Would that be correct?
Absolutely right. So for the mixture of Gaussians, that would be most useful for continuous data. But if the data is already discrete, or if you've created a grid where you're approximating the continuous data with discrete values, you're exactly right. Now you can assign any probability that you want to the discrete set of values, and it doesn't have to follow any particular analytic function or any particular shape. It's just an arbitrary set of probabilities.
Cool. All right. Our next question is about your book. And so I think there are a lot of people who would really love to go check out your book. And I think it might be helpful to maybe answer this first question and then also give a bit of an overview of what your book talks about. So the specific question are there more technical or algorithmic issues with Bayesian methods that you cover in Think Bayes? And then maybe after that, tell us a little bit more about your motivation for Think Bayes and a few words on encouraging us to read it.
Sure, yes. So about the technical issues that come up, the book is based on a series of case studies. So it is intended to be very practical in the sense that for each case study, I develop a solution, and usually more than one solution, because you always have to make modeling decisions. So usually I'll start with the simplest possible model and then start to add more features to it in order to see, what can we leave out and what do we have to include in the model in order to get a credible model, a credible set of predictions. So the issues that come up are sort of as they arise in order to solve those case studies. I should say I'm in the process of working on the second edition of Think Bayes. So the first edition is all grid algorithms. I actually don't use PyMC or any MCMC in the first edition. The intention there is to help people get started, to understand Bayesian methods by doing these grid algorithms, and then they would be prepared to get started with PyMC. What I'm working on now with this example is the second edition, where I really want to try to make that connection much more explicit. And for each case study, show the solution using both the grid algorithm and PyMC. Because I think that'll help people get started, but it'll also get them to the point of using what's really a professional grade tool that can solve large, difficult problems. At some point with grid algorithms, you get to the end of the road and you have to switch to MCMC.
Yes, definitely. And for those of you who are a little bit curious about PyMC 3, right now it's based on Theano, and so it's Conda installable. So if you have the data science package manager, the Anaconda distribution of Python, then you can actually Conda install it. I'm on the development team right now, and we're actively developing PyMC 4, which is based on TensorFlow probability. And so stay tuned for, I don't know how long it's going to take, but stay tuned. There's active development on GitHub for that. Also on Allen's book, I'll give a firsthand testimonial. I actually learned Bayesian methods through Allen's first edition of the book. So I'm really looking forward to hearing about the second edition and how it incorporates PyMC into there. So the next question here is about the relationship between Monte Carlo and Bayesian methods. And I'm wondering, Allen, if you could speak to a little bit about that. I think there might be a bit of confusion out there with these terms being thrown out. Maybe a little clarity could help us in our learning journeys.
Sure. So Monte Carlo gets used broadly for almost any kind of randomized method. So the example, the first forward problem that I did, where I simulated hockey games by drawing values from a random distribution, you could call that a Monte Carlo simulation of a hockey game. And I used it in order to estimate the distribution of goals scored. So Monte Carlo by itself is a very general term. MCMC, the Monte Carlo Markov chain algorithm, is what is built into PyMC. And it's how PyMC does the inference problem. And it's Monte Carlo in the sense that it is randomized, and it is Markov chain in the sense that it is following a sequence of steps, moving through the probability space and evaluating the probability density at each of the locations that it moves along in this chain. Eric, do you want to add to that?
I guess the way that I think about, yeah, definitely. The way I think about it is Monte Carlo methods are but a tool in the toolkit for Bayesian modelers. If you go deep into the math, and I don't want to do that today, but if you go deep into the math of Bayesian methods, you'll see lots of integrals. And boy, those integrals are hard to read and hard to solve analytically. So Monte Carlo methods allow us to sidestep doing the analytical math part and just use random sampling to help us figure out what our posterior distribution looks like. And that's really how I would say what the relationship between Monte Carlo methods and Bayesian methods are. Anything else from you, Allen, on that?
No, that's good. And that actually reminds me, that is the magic of MCMC, is that you can generate a sample from the posterior distribution without ever computing the posterior distribution.
Oh, right, yes.
Which sounds strange, but that is exactly how it works.
Yes, that's right. Okay, so we're going to go to a little bit more of a meta level question. I think there's interest in the community about Bayesian methods and artificial intelligence and machine learning. I'm wondering, where would you place these three categories in relation to one another?
Right. This is not my area of expertise, so I'm going to try not to say anything wrong. But I will say that
all right.
For many of the problems that people solve using machine learning and AI, Bayesian methods are an option. You can use them to do things like classification and other classic machine learning problems. Many machine learning algorithms are effectively an approximation of a Bayesian method. So sometimes the Bayesian method is, in some sense, the gold standard, and there are other algorithms that approximate it and might be more efficient or might have other desirable properties. So I guess if I'm drawing the Venn diagram, there's an overlap. So you can use Bayesian methods to solve machine learning problems, but there are other machine learning algorithms that are not Bayesian, and there are other things to use Bayesian for that are not machine learning.
Okay, cool. And I think I don't want to take too much away from your excellent webinar today, but there are people who have been working on what we call Bayesian deep learning. and it's a really active area of research. And if you're mathematically inclined, I'd really encourage you to go take a look at those, because deep learning, as we know, falls under the umbrella of machine learning. And now there are individuals, research groups that want to take ideas from Bayesian statistical modeling and apply it using, deep learning algorithms, or rather deep learning models, as the so-called thing that they apply Bayesian methods to. And so there's a wealth of talks and papers that are out there that you can take a look at your own leisure as well. All right, Alan, so we're gonna go to the final question for today. And this one is back into the land of modeling, because I think this is a really great question that's very practical and applicable for people who are doing modeling. And that's how we diagnose whether our model is performing well or not. So, we can specify likelihoods, we can specify our priors, we can specify the link function between the priors and the likelihood. However, how do we tell whether we've got it right? Or whether, maybe in another way, how do we tell whether we've done something wrong?
Right, great question. I think of it at two different levels. Part of it is validating your model decisions, and the other part is validating your implementation. So model decisions means that you have included the things that need to be there, and that the things that you've left out, it's okay to leave them out. The errors are small. One of the ways to do that is by running multiple models and comparing them. And I talked a little bit about this earlier. The case studies in the book, I often start with something very simple and gradually add one feature at a time. If I add a feature and I find that the results are wildly different, that is a signal that I need to think carefully about that modeling decision, and that new thing that I just added is important. If I make the model more complicated and the results are basically the same for practical purposes, then I would say, okay, look, I don't need the complicated model. The simple model is probably good enough. So that's part of it, model comparison. Part of it, I find, visualization is hugely important. If I can find a way to represent the inputs and the outputs in a way that I can visualize and interpret in the context of the problem, then issues, become visible. And one example of that, just taking the hockey example, is if I've got teams that are scoring 20 goals in a game, I know from my background information that that's not likely, but I need to make that part of the model visible so that I can see that problem. So that's part two is visualization.
Okay, actually that does remind me, because you use this the posterior predictive sampling function in PyMC3, and that actually lets you simulate data from your model that was conditioned on the existing data. You can actually check whether the generated data have roughly the same distribution as the original simulated data by doing either a CDF check or probability histogram check, whichever floats your boat. But I personally would recommend CDFs, just like Allen does. So you can do those. You can use those visual checks to help you with diagnosing the model. Okay, cool. We are a bit out of time now, and so there are a lot of questions in the Q&A. If I'm not mistaken, we'll be able to take those and put them on the discourse site, and we can continue the discussion over there. Meanwhile, thank you for your time, Allen. Really appreciate all the effort that you've put into this. The link to the talks will be available, are available, as you can see on this on your screens. The talk recording will also be made available, and everyone who's registered for this webinar will gain access to it. All right, thank you very much, Allen.
Thank you, Eric. It was great having you both moderate and also help answer questions. I really enjoyed it.
My pleasure. See you, everybody.